This is Angela Galloway, and this is a lecture for Math 146. This is Chapter 12, which is actually our Unit 4, so our last unit in Math 146. And so Chapter 12, actually we're going to get into a lot of topics, which is why usually I spend a lot of time on this chapter because there is a lot to go over in this chapter. We have several sections and several different concepts that we'll cover. So in chapter 12, what we're talking about is statistics, okay? And statistics covers a wide range of information, okay? In general, statistics is the science of organizing and summarizing information to draw conclusions or answer questions. What I like the most about this section is that statistics is something that's used everywhere, every day, okay? And so we can find lots of real world examples to use when we're in this chapter because statistics is really something that you will use every day. You know, sometimes it's hard for me to tell you where you're going to use um, graphing or maybe even the voting procedures that we talked about or some of the other topics that we've gone over. But I can show you pretty easily where you're actually either going to be calculating statistics or learning or hearing about statistics in your general everyday life. So some examples of that with business, when we talk about statistics, business use statistics in forecasting when they're trying to plan their inventory or their shipments or their sales or any of that, you know, they use forecasting for. They usually have a whole forecasting department, and that's what I actually used to do before I was a teacher full time. I used to do forecasting at Fruit of the Loom, and you know, so I know that we used a lot of statistics there. In manufacturing, in business, there's something called Six Sigma training, which you may have gone through yourself. I know I went through the Six Sigma Green Belt training, and that uses concepts from statistics to figure out, you know, when they're having an issue in manufacturing. Okay, in the medical field or healthcare, we hear about clinical trials and experiments, you know, when they're trying to figure out if a new therapy is better than an old one or if a new drug is better or what kind of repercussions we might have from changing to a certain new drug that maybe we've heard about. Those are all figured out by using clinical trials or experiments. And the way they figure out if one thing is better than another is by using statistics. Then in sports, often when you say the word statistics, people will kind of think about sports because they hear about, you know, like the players' statistics or the team stats or whatever. They have a team statistician. And so definitely stats are used there. They're typically descriptive statistics where we're just trying to describe how good of a player or how good of a team they are. So rankings are done using statistics. If you think about, you know, football, free throw, or basketball, I think is when I wrote these, thinking about free throw percentage. But if you're talking about football, looking at quarterback rankings or pass completion rates, that kind of stuff. Now, with the politics and media, that's something that's very prevalent right now because we are in the middle of an election year, and so we're seeing lots of polls, but also just doesn't have to be with politics. I mean, there's polls about everything. You know, how do you feel about blue cars or whatever? You know, I mean, there's a poll every second, it seems like, that comes out asking people how they feel about something. So we see those a lot with that. Okay, so we're going to hear polls. So, like I said, even if you're not actually calculating statistics, like if you're not in the forecasting department or you're not doing some sort of clinical trial, you still are probably hearing statistics every day. And so, what we want to learn is how to understand them, how to think about what they're telling us because we don't want to just accept, you know, whatever they tell us on the news every night. You know, you shouldn't just hear them say, oh, this poll said this, so that must be true. You know, you want to start critically thinking about, does that make sense? How did they get the poll? Who was asked these questions? What kind of questions did they ask? And then decide from there if you think the number makes sense or not. So knowing how to calculate stats is good, but understanding and being able to explain those statistics is much more important. Let me close my email there for a second so I won't keep getting messages. Um, So what I want you to understand more from this chapter is how to explain statistics, how to critically think about them, and not necessarily just, oh, I have to memorize this formula or I need to, be able to punch this into my calculator, but think more about what does it mean, okay? So what does my answer mean when I get to the end? And that's kind of the difference I see in like a math class and a statistics class. In a math class, you might get to the end of a problem and you've solved the equation and you get x equal 5, and then that would be the end, right? You'd say x equals 5, I'm done. But in statistics, once we get to the answer, then we start looking at, why did I get the 5? Is that what I expected to happen? Is that a good result or a bad result? And then I try to interpret the answer. So we really do think of it more in real life terms of, what does this number mean in this situation? So that's kind of the difference in a math, base class and more of a statistics class. So in section 1, which is the first section of this chapter, we're going to talk about visual displays of data. And so the first thing we look at is there's two divisions of statistics. One is descriptive statistics. Descriptive stats is just an organization and summarizing of information. So it's when we do graphs, charts, tables, calculating an average or whatever. That's all just descriptive statistics. You're just describing the data that you have. Inferential statistics is the higher level of statistics, and that's when you are trying to use the information you got to infer something about an entire population or an entire group. And so to talk more about inferential statistics, we kind of have to go over a few definitions. So the first one is the difference in a population and a sample. Okay, so we have a population and a sample. A sample is the part of the population from which information is usually obtained. We typically know what a sample is. If they say I did a poll and I took a sample of 1,000 people, that's a sample, right? 1,000 people were chosen. The population, though, is the collection of all individuals or items under consideration in a statistical study. So that's the information that you actually want. You actually want to get the information from the entire population, but typically we don't have the time or the resources to be able to contact the entire population. So instead, we take a sample, which is a smaller group from the population, and we collect data from them. Okay, if we are able to get information from the entire population, the information that we get is called a parameter. So a parameter comes from the population. A statistic comes from the sample. So a statistic is calculated using data from the sample. Okay, and so I usually tell my classes that parameter goes with population, statistic goes with sample, and the nice thing is they start with the same letter, right? So population and parameter go together, sample and statistic go together. So this is a little drawing you can kind of do to think of, what does this population and sample mean? Okay, so let's say that we are going to do a poll about the percentage of people who are going to vote for Donald Trump. Okay, so what is our population? Well, the people that we want information about are, let's say, all U.S. voters, right? That's who we want to know about. But if I really wanted to find how all U.S. voters were going to vote, it would be very time consuming, right? It'd take me a long time to go out and ask every single U.S. voter, are you going to vote for Donald Trump or not? So it would take a lot of time, it would take a lot of money to do that. And by the time I get that information back, the election would probably already be over, right? So it would be useless to do that at that point. It'd be useless to tell you about my poll when the election had already happened. So instead of asking all U.S. voters, what I'm going to do is I'm going to take a sample, okay? And so a sample is a smaller group from the population. Now we want this sample to be a good representation of the population. Okay, we don't want to go out and just sample the first 1,000 people we run into. We don't want to sample just Kentuckians. We don't want to sample just Republicans. We don't want to sample just women. You know, we want our sample to look just like the population, but just be smaller. Okay, so we want a good mix of ages, races, genders, states, etc. Okay, we want a good mix in our sample so it represents our population well. So we're going to take this sample of 1,000 voters. From those 1,000 voters, we're going to ask them, you know, are you going to vote for Donald Trump or not? Okay. And then we calculate a statistic. So let's say we ask them that and we find out that 31% of our sample said they're going to vote for Donald Trump. Okay. So that is our statistic. All right, that is the data that came from our sample, so that's why it's called a statistic. Now, using inferential statistics, what the nightly news is going to say is they're not just going to say 31% of our sample said they're going to vote for Donald Trump. They're probably going to say 31% of all U.S. voters are going to vote for Donald Trump. And so when you hear those polls, you may have thought, well, I don't know how they know what all U.S. voters are going to do because I did not vote in this poll, right? So how do they know what all U.S. voters are going to do? Well, the way they do that is they figure that if they take a good sample that's representative of the population, when they get this statistic, they can use inferential statistics to say that I think this is a pretty good sample from the population. So I'm going to infer that the true parameter, so the true percentage of people that are going to vote for Donald Trump, is probably pretty close to the statistic that I got from my sample. So they're going to say 31% of our population are going to vote for Donald Trump. So they're using this statistic to infer about the parameter. And that's what inferential statistics is, okay? It's using our statistic to infer about the entire population. So how do we collect data? Well, there's two types of studies that we will see. One is observational studies, and they just observe characteristics or just ask questions. That would be polls. You know, polls would be an example of an observational study. There's other examples, but polls are the most common that we know of. Experiments impose a treatment on the subject and then record the results. Okay, so they you know, force someone to try a new treatment, or they, you know, if we're looking at making plants grow taller, we give a certain amount of the plants a different soil or give them different amounts of water or whatever. So we're imposing some sort of treatment on them, and then we observe what happens at the end. Okay, experiments are often preferred because they can show a cause and effect relationship. Observational studies can show that two variables are correlated, but they can't prove that one variable caused another variable to occur because there are lurking variables, okay? And so one study that we look at is this theory of the stork. Okay, so there's this theory here that says, do storks deliver babies? Okay, well, we all probably know that storks don't really deliver babies, right? But if you look at this, if we just compare birth rates and stork populations, and this was in, I think, Germany, at least the one I looked at, looking at the relationship between stork populations and human birth rates, we actually see that it is pretty highly correlated, okay, which means that it looks like as X goes up, Y goes up. So as the number of stork breeding pairs goes up, the birth rate goes up. So does that mean that storks are bringing the babies? Well, no, probably not, right? Because we know that that's not true. However, just using that observational study, just observing that data, it does look like one is causing the other to happen, right? So how do we show that that's not true? Well, in this case, it's easy to show that's not true, right? We just say, well, has anyone had their baby brought by a stork? No. You know, so we know that's not true. But with other situations, sometimes it can be difficult to figure out, is it true or not? For example, if we were just looking at observational studies with autism and vaccination rates. Now, just looking at the pure, just regular data, vaccination rates are going up and so are autism rates. Well, does that mean that one caused the other? Or could it be that just both things happen to be increasing at the same time. We would have to have an experiment to be able to show that one's causing the other. Because what's happening is there's lots of confounding or lurking variables in the background that could be causing these outcomes. So, for example, with the storks and the babies, what was happening at the time was that in Germany, they were starting to protect the wetlands where the storks were breeding, and so the stork population started going up. At the same time, what that graph was actually measuring was the number of home births. So the number of babies that are born outside of a hospital. And so that birth rate was going up because, kind of like here in America, home birth was starting to be uh, more talked about or whatever, and so they were having more home births. So something was causing the home births to go up, something was causing the stork populations to go up, but they really had nothing to do with each other. There were just outside lurking variables that we weren't measuring that were causing these things to increase. So what I want you to think about with this is that if you hear that something is done with an observational study, okay, not an experiment, then you can definitely show that two things are related, but it might not mean that one caused the other to happen, okay? And we'll get more into that as we get into the rest of this chapter. But while we're talking about this is experiments would be preferred, right? Because then we can show that one thing caused the other. However, not all studies can be done with experiments. And so I asked the class, why not? And one of the main reasons is it might not be ethical. For example, what if we want to prove that texting while driving can be fatal? Well, do I want to do an experiment with that? Like, do I really want a real life experiment where I force people to go down the road and text while driving and see if they are killed or not? Well, probably not, right? So I would either find another way that I could simulate the texting while driving, maybe as an experiment, or I would look out observationally. I would go and say, okay, these wrecks happened. How many of these wrecks had people that were texting while the wreck occurred? And that would lead me to believe that, this many accidents had texting, this many didn't, whatever, and I could make some conclusions off of that. Also, something like smoking and pregnancy. We're already aware that smoking while pregnant is not a good thing, but would you want to say, okay, I've got 40 pregnant women here, I'm going to make 20 of them smoke, 20 of them aren't going to smoke, and then we're going to see what happens with the babies? Well, obviously not, because that's not ethical to do, right? So not all studies can be done by experiments, but if it's possible, we would rather do an experiment so that we could show that cause and effect relationship. Okay, so let's look at just a basic example where we're trying to identify the sample in the population. So local electric company wants to know if their customers are satisfied with their service. They send out 1,000 questionnaires to a randomly selected group of customers. 62% of the customers questioned said they were satisfied with their service. So the population that we want information about is all the customers of this electric company. Usually when we're talking about the population, we're going to have the word all in there. So here we're talking about all customers of the electric company. The sample is usually the number. So here it says they send out 1,000 questionnaires. We're going to assume that they get all 1,000 of those back, which doesn't usually happen, but let's just pretend like it's a perfect world and everybody sends back their questionnaire. So the sample would be about 1,000 customers. The parameter is the proportion of all customers, which is our population, who are satisfied with their service, right? Because that's what we were looking for here. And then the statistic, the information we actually got back from our sample, 62% of the sample said they were satisfied with their service, so that would be our statistic. So the parameter, we actually don't know what it is. We don't know the actual percentage. We're just explaining what it would be if we could get that information. Okay, this one again, we're looking for the population and thinking a little bit more about if we would trust this situation. So it says the highway planners decided to make a main street in West Lafayette, Indiana, a one-way street. The Lafayette Journal and Courier took a one-day poll by inviting readers to call a telephone number to record their comments. The next day, the paper reported our readers overwhelmingly preferred two-way traffic flow by a margin of 7 to 1. Of the 98 comments received, all but 14 said no to one way. So the population they would want information about was all residents of West Lafayette. Now, did they actually get a sample from all residents of West Lafayette? Well, they got 98 people, right? But did they ask all residents? I mean, did they include everyone? Did everyone have an equal chance of being chosen for this survey? Well, not really, right? So this is one of the reasons we might not trust this survey. So if our population is all residents, did our sample come directly from all residents? No, right? Our sample actually came from newspaper readers. So what we would call this green thing here is the sampling frame, okay? Because the sample actually came from the newspaper readers, not from all residents. And so why that might be a problem is newspaper readers might have something in common that excludes other residents of the population. So, for example, maybe most newspaper subscribers are older residents, or maybe most of them live outside the city, or maybe most of them have a job, or maybe most of them whatever. Okay, so for whatever reason, that might have something to do with the way they answered the question. And so that might mean that our sample is not representative of the entire population. The other issue is whenever you choose yourself for a survey, that's called voluntary response. And what voluntary response means is like if you go to ESPN.com today, there will be a poll there that you can choose to take, right? If I choose myself for the survey, then that means I have volunteered to respond to that survey. It's called voluntary response. Now, that's going to skew our results more than if I had randomly chosen people, okay? Because typically the people that choose to do a poll are the ones that feel the most negative about it, okay? Or have the most strong opinions. So in this case, you know, if there were some people that were really concerned about this Main Street being turned into a one-way street, they're probably going to make sure that their comments are heard and that they call in. If you just have a regular everyday reader that's reading about this and they don't really care if the street is one way or not, they're probably not going to call in and make a big deal about it because to them it doesn't really matter. So it might look like more people are opposed to it than really are in the population because they did not randomly sample a group from the population. Okay, some more definitions that we go through, and that's what we do a lot in this first section is just getting some definitions out of the way so we can start actually calculating some statistics. So we have a variable, just in general, as a characteristic that varies from one person or thing to another. There's two types of variables that we talk about. We have quantitative and qualitative. Qualitative are also called categorical. They're same thing, just two different words for the same thing. So for categorical or qualitative, we're talking about words, okay, word groups. Oh, excuse me. So it's a non-numerically valued variable. So examples are gender, race, scales, like 1 to 10, like how happy are you, something like that. Yes, no, all those are going to be categorical or qualitative variables. Quantitative variables are a numerically valued variable, so those would be age, height, weight, time, anything with numbers pretty much. Except for the scales, the 1 to 10 scales, generally anything with a number is going to go in the quantitative. So identify the variables as qualitative or quantitative. So some of your homework is just going to be like this. You're just identifying what type of variables we have. So class year, thinking of freshman, sophomore, junior, senior, etc. Would that be qualitative or quantitative? Well, that's going to be qualitative because that's going to put people into categories, right? It's going to put you into groups. So that would be qualitative. Your race, that would be qualitative also, right? Because that's putting you in a certain racial group. Listing price for a house is going to be quantitative. That's obviously going to be a number. And then birth year, again, that would be quantitative. That's going to be a number, right? Okay, so I think I'm going to stop this one right here just because it's already kind of long, and we will get into how we're going to start organizing this qualitative and quantitative data, putting them into graphs and all that in the next section.